Good afternoon. This file contains the pre-lecture slides for class on Tuesday, September 10th. The relevant reading for this pre-lecture focuses on sections 3.1 through 3.9 of the 8th edition of the Carey textbook. As an added bonus, I've also included content taken from sections 4.2 and 4.3 to build on what you learned last week. These sections include additional IUPAC naming rules that you'll need to use to name alcohols and alkyl halides. You'll see examples of these types of functional groups used in Chapter 3, and it's helpful to know how to name them in advance. So, the takeaways from this lecture on Chapter 3 focus on conformational analysis. Conformation refers to the different spatial arrangements of a molecule that come about from rotation about single bonds or sigma bonds. Different spatial arrangements produced by rotation are referred to as conformers of one another. If the molecule in question is cyclic, we refer to conformers as cyclic conformers. Conformational analysis involves identifying the various types of energetic strain produced by rotation around sigma bonds when ideal bond angles and bond lengths are distorted. There are three types of strain we will cover in this lecture: torsional strain, steric strain, and angle strain. We'll begin, however, by reviewing those IUPAC naming rules for the two functional groups so that you can recognize the names of some compounds that are included in this presentation as well as in Chapter 3. Of note, alkyl halides, recall, are organic molecules that contain a halogen functional group, and alcohols are organic molecules that contain an OH functional group. Okay, first, nomenclature. Your book introduces you to two different types of nomenclature: functional class nomenclature and substitutive class nomenclature. For our course, we're going to focus on substitutive nomenclature solely. Unfortunately, the course textbook uses both kinds of nomenclature haphazardly throughout, so it's a good idea to familiarize yourself with functional class nomenclature as well, just so that you're not confused by the molecule name that Carey introduces if he tends to use functional class nomenclature. We'll compare both approaches for alcohols and alkyl halides on the next few slides. Okay, first, alkyl halides. Remember, alkyl halides are any alkane compounds that have a halogen substituted for one or more hydrogen atoms. Functional class nomenclature uses the following rules. The name of any compound includes two words. The first word indicates the name of the alkyl group attached to the halogen, following all the rules we covered last week around naming simple alkanes. The second word includes the name of the halogen in the molecule as a halide. So roughly, functional class nomenclature for alkyl halides have the form alkyl as the first term, halide as the second term. Let's look at the example on this slide. First, okay, we identify the longest chain that starts at the point of attachment to the halogen. So we start here. Okay. If we count, we have 1, 2, 3, 4 carbons going to the right. Let's try the other side. Starting again here, 1, 2. So the longest chain is 4 carbons long, which makes it a butane. Okay. Coming off position 1, there's a methyl group. So the alkyl group here is 1-methyl-butyl, okay, and it's attached to a fluorine, so the name is 1-methyl-butyl fluoride. Again, 1-methyl-butyl fluoride. Okay. Substitutive naming, in contrast, uses the name in the form of a haloalkane, where the halogen substituent is listed as a prefix before the name of the alkane that it's attached to. This naming system is a little bit simpler. So let's take a look here on this slide once again. Okay. Now we count the number of carbons in the longest chain of the alkane, starting from the end of the alkane. Okay, so let's just start from the left. 1, 2, 3, 4, 5. Could start from the right. 1, 2, 3, 4, 5. No matter which direction I count in, I get 5 carbons, which means that the longest chain here is a pentane under substitutive naming rules. At position 2, we have a fluoryl group coming off. There's a fluorine there, so we append it as a prefix before the name of the alkane, and this becomes 2-fluoropentane. Remember the rules from last week. You always number the chain from the end of the chain closest to the first substituent. So here we have only one substituent, which is the fluorine group. So we start counting from this end. If we number them, 1, 2, The locant is 2, so this is 2-fluoropentane. Same as naming any branched alkane. Here on this slide, I've included for you the 4 halogens, as well as their names, the name of their halides, as well as the prefixes that we'll use in substitutive naming nomenclature. So fluorine becomes fluoro as a prefix, chlorine becomes chloro as a prefix, bromine becomes bromo, and iodine becomes iodo. Okay. Note, a lot of people misspell fluoro. The U comes before the O, not the opposite way around. Let's look at one more example of this, this time a cyclic example. Okay, once again, using functional class nomenclature, you would count the number of carbons, okay, starting at the point of attachment to the halogen. Okay, 1, 2, 3, 4, 5, 6. These are in a cyclic structure. So as a functional class, the alkyl group would be a cyclohexyl group. It's attached at the first point of connection to the bromine, so this would give us 1 cyclohexyl bromide. Okay. Using substitutive nomenclature of the form haloalkane, okay, we once again count the number of carbons, 1, 2, 3, 4, 5, 6. 6 carbons means this is cyclohexane, but now we put the halogen as the prefix instead of the alkyl group, and we get 1-bromocyclohexane as our name. Okay. So the question often comes up about what do I do if I have a name to name a branched alkyl halide. Okay, in cases where a compound has multiple substituents of different kinds, as we see here on this slide with a branched alkyl halide, both substituents must be individually listed as prefixes before the basis of the name. We place them in order starting from the substituent closest to the end of the chain, same as we did before with branched alkanes. In cases where both substituents are equidistant from the ends of the longest chain, we use alphabetical order to decide what order to list them in. So we just take a look at this example down here at the bottom. Okay, let's count the longest chain from any end. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. 5 carbons in either direction. Let's try again. 1, 2, 3, 4. That's 4, not as much as 5, so we don't count that. Any others? Oh, one more. 1, 2, 3, 4. Still 4 is less than 5. So the basis in this case is a pentane for 5 carbons, and I'll go ahead and circle that for you on the slide. So there's your basis. Okay. And you got 2 substituents coming off here. Right. We'll just put our cut points in there. Okay. Down here a fluoral group, and up here a methyl group. Okay. Remember, you count your, you number your carbons from the end of the alkane closest to the first substituent. So this fluorine is only 1 carbon away. The methyl group is 3 carbons away from either side. So we start counting from the left. 1, 2, 3, 4, 5. Okay. And we order them, okay, in the name, okay, from the end that's closest to the, or from the substituent that's closest to the end. So in this case, we have 2-fluoro, 3-methylpentane. Okay. So we name alcohols using the exact same rules for functional class alkyl halides, except ending in the name of a halogen. We end the name with the second word as the word alcohol. Okay. So let's look at this example here for functional class nomenclature of alcohols. Okay, once again, alkyl plus alcohol instead of halide. Okay, otherwise it's the same. Start up here counting 1, 2, 3, 4. Okay, off of position 1, there's a methyl group. So the alkyl group is 1-methylbutyl, and there's an OH group attached at that position. So we know that this is 1-methylbutyl alcohol. Okay. Substitutive nomenclature for alcohols is slightly different. Generically, we name them as alkaneols, as you see here. Okay? What that means is the name begins with the name of the straight chain alkane of the same length as the alcohol, except we remove the E from the end of that name and replace it with the letters OL to indicate the presence of the alcohol functional group. Notice that we also include the locant for the alcohol group in the name, and it can go in one of 2 places. It's perfectly reasonable to put the locant before the name of the alkanol, so 2-pentanol. Or alternatively, you can put the locant number before the letters OL, and in this case it becomes pentane-2-ol. So 2-pentanol or pentane-2-ol, these are synonymous with one another. Okay? Note that in any case where an alcohol or an alkyl halide has its functional group at locant position 1, we do not include the number 1 under substitutive nomenclature rules. If you ever see the case of a alkyl halide or an alcohol that doesn't have any numbers indicated, you know by default that that means it is located at locant position number 1. This is only true for substitutive nomenclature. This is not true for functional class nomenclature. Remember, we're going to be focusing on substitutive nomenclature in this course. Okay, what do we do when we name branched alcohols? Okay, same rules as always, one small change. Okay. In branched alcohols, the alcohol substituent must always receive the lowest number, the lowest locant number, opposed to any alkyl groups that are in a chain. That is, they are high in priority. Okay, so in this case, if we identify the longest chain here, starting with 1, 2, 3, 4, 5 carbons, okay, so we know it's a pentanol. And to number this, we always number from the end of the chain closest to the alcohol. So we number from the left. 1, 2, 3, 4, 5. For this structure, we can't number it from the right side because the right side is furthest away from the alcohol. If the alcohol were instead closest to the right side, we would number it from the right side of the structure. Okay? So in this case, this is a 2-pentanol, and also coming off of position 3, we have a methyl group up here, which means the name of this compound is 3-methyl-2-pentanol, or alternatively 3-methyl-pentane-2-ol. It cannot be 3-methyl-4-pentanol, though, because that would be numbering from the right side, which we can't do. Remember, the alcohol needs to receive the lowest number, the lowest locant, because it's highest in priority. Okay, what do you do if you have multiple functional groups of different kinds in alcohols? Alcohol substituents always receive the lowest number, lower than any alkyl or any halogen group. Remember, alkyl and halogen groups both tie with each other in terms of numbering, and you just place them in order of the alphabet if you have an alkyl group and a halogen coming off. However, with an alcohol, you've got to make sure that the alcohol has the lowest locant number. So if we look at this example here, you'll see that again we have a pentane, 1, 2, 3, 4, 5. But for this compound, we're going to number it from the right for our locants because the alcohol group is closest to the right terminus of the chain. So this compound becomes 4-iodo-2-pentanol, not 2-iodo-4-pentanol, because in the bottom, this name would be giving the higher number to the alcohol. We want to put the lowest number next to the alcohol. Okay. Those are the rules that you have for naming alcohols and alkyl halides. We'll do this in more detail when we get to chapter 4, but at least at this point, whenever Carrie introduces any alcohols or alkyl halides to you in chapter 3, you'll recognize their names. So let's talk about conformational analysis, okay, now that we've got the names of alkyl halides and alcohols behind us. All right? As stated previously, conformations are different spatial arrangements of a molecule that are generated by rotation about single bonds. Okay? The same molecule that undergoes rotations around its single bond can assume new structures that are called conformers of one another. Okay? So who cares about this? Why do you want to learn about conformers? Okay? Before we get into the detailed discussion of conformational analysis, I'll quickly highlight why you should learn this. So remember what I've said before. Structure is everything in organic chemistry because if we understand the structure of a molecule, we can understand and predict the chemical and physical properties of that molecule. Conformational analysis is one approach to understanding structure because it helps us better understand the relationships between the spatial arrangements of atoms in a molecule and the molecule's properties. If we take this example to a large scale, many proteins in our body only function appropriately when they assume very specific conformations. For example, on this slide here, I have a ribbon diagram of the same protein in 2 different conformations. Okay? This example illustrates what we know about the relationship between mad cow disease and conformation of proteins. Mad cow disease is believed to be caused by infectious agents known as prions. Prions are rogue conformers of proteins that have their atoms spatially arranged in an abnormal way that makes them stable to degradation and increases their potential to disrupt normal biosynthetic processes in a healthy organism. We can understand the process by which a rogue conformer forms by conducting simple conformational analyses on small organic molecules here in the first semester. Whether molecules are small or large, all of their conformers result from rotation around sigma bonds in organic structures, and a rogue conformer of any protein can be seen to result from the incorrect rotation of many hundreds of sigma bonds within that protein. So, there are two types of conformers that we will concern ourselves with here in 232. Okay? Eclipsed conformers, as illustrated on this slide, are those in which all of the adjacent bonds on two carbon atoms in a structure are completely overlapping or aligned with each other, thus we say that they are eclipsed. So here on this slide, you can see in the 3D structure on the wide face, also represented with the dash wedge perspective formula at the bottom, and end on here on the right side, same molecule just turned 90 degrees, represented down here with a Newman projection. All of the hydrogen atoms are perfectly aligned with each other on the two adjacent carbons in ethane. Thus, this conformer is called the eclipsed conformer of ethane. Notice down here in the Newman projection, we draw the hydrogens on the back slightly to the right or left of the hydrogens on the front carbon, because otherwise they would be perfectly aligned and we wouldn't be able to see them. Learn to recognize that when you see this Newman projection, it's an indication of an eclipsed conformer when the hydrogens are fairly close to one another. In contrast, staggered conformers are those in which all of the adjacent bonds on the two carbon atoms adjacent are arranged at the maximum possible distance from one another. These conformers are said to be staggered because the adjacent bonds alternate in an up and down fashion. Again, we can see in this model of ethane, all adjacent hydrogens are spatially arranged in such a way to produce a staggered conformer. So if we look at the 3D model, right, this hydrogen is staggered from this hydrogen. This hydrogen in the back is staggered from this here in the front, and this in the front on the right is staggered from this one on the back, okay, as represented down here in the dash wedge formula. In the end-on perspective of the model, what we can see is that none of the hydrogens are overlapping. They're 60 degrees apart, as far apart as they can be, as illustrated in the Newman projection down here. If you have a model kit, it's helpful to build a structure of ethane and to rotate the sigma bonds in ethane to prove to yourself that the staggered conformer has this shape as seen here, and the eclipsed conformer has this shape as seen here. With regard to staggered conformers only, there are two spatial relationships between adjacent substituents coming off of the carbon atoms that we have to learn. Okay? Those are anti-relationships first, as seen here. Two bonds are said to be anti one another when the angle between them is 180 degrees. So as indicated, what you can see is the red hydrogen with the box around it is 180 degrees away from the blue hydrogen on the adjacent carbon in the back. Okay? Thus, the blue and the red hydrogen have an anti-relationship. You notice that there are two other pairs of hydrogens in this structure that also have anti-relationships. See if you can identify them. The second spatial relationship is a gauche relationship. A gauche relationship exists only for staggered conformers and is the relationship between two adjacent atoms that are 60 degrees from one another. So as you can see here in this diagram, in this staggered conformer, this blue hydrogen, okay, is 60 degrees away from this red hydrogen, right? Thus, these two hydrogens are said to have gauche interactions. Okay? There are 5 other sets of gauche interactions or gauche relationships in this staggered conformer. See if you can identify all 5 of them. Okay? Remember, an important point, the terms anti and gauche apply only to bonds or adjacent carbons that are in staggered conformations. Okay? It's specifically in terms of adjacent carbons and staggered conformations. You can't have anti or gauche relationships in an eclipsed conformer because in that case all of the bonds are aligned. So an important question to ask yourself is which one of these conformers is more stable? Is the eclipsed conformer more stable or is the staggered conformer more stable? To answer this question, we conduct a conformational analysis to determine the relevant differences in internal energy between each of the conformers to determine which one is more stable, right? The one that has the lowest energy. Before we review how to conduct a conformational analysis, just take a guess. Which do you think will be more stable? Do you think it's the eclipsed conformer, where all of the bonds and atoms are perfectly aligned with each other, or the staggered conformer, where all bonds and atoms are as far away from one another as they can be? What you've already reviewed from general chemistry about VSEPR theory should help give you an educated guess about which one you think should be more stable. Let's conduct a conformational analysis, though, on ethane to see if we can prove it to ourselves. To do a conformational analysis, we have to examine three types of strain that exist within any molecule related to the distortions of bond angles and bond lengths. Okay? First, torsional strain is the strain that results from bonds when they are eclipsing one another. Torsional strain refers specifically to bonds, the electrons that are in bonds. Okay? Van der Waals strain, also known as steric strain, as noted in your textbook, results from atoms being too close together. Okay, so if torsional strain results from electrons in bonds eclipsing, steric strain or van der Waals strain results from atoms being too close or eclipsing one another. Okay. Angle strain, the third type of strain, is strain that results from the distortion of bond angles from their normal values, and for this class we're going to focus on angle strain in cyclic molecules specifically. So let's look at each of these in detail. First, we'll examine the concept of torsional strain. Okay, so first, let's look at some data. Experimental data reveals to us that the eclipsed conformation of ethane is 12 kilojoules per mole higher in energy than the staggered conformation. Okay? This data tells us right away that the staggered conformer is more stable than the eclipsed conformer. Is that the one that you guessed would be more stable? Okay. The explanation for why the eclipsed conformation is destabilized relative to the staggered conformation comes from an examination of torsional strain in the structure. Okay? Because the adjacent CH sigma bonds in each carbon in ethane are eclipsing one another, the electrons in each of those sigma bonds are brought together in very close proximity. Remember that electrons repel each other, and by bringing them into close proximity, you put strain on the molecule because the electrons are forced closer together than they are ideally located. Right? Once again, this type of strain is called torsional strain when we're referring to the overlapping of bonds or electrons in bonds. If we examine multiple conformations of ethane, we can see that there's a sinusoidal curve that defines the relationship between the internal energy and the dihedral bond angles. So starting from the upper left, we've got an ethane molecule here, and I've just color-coded the hydrogens to make it easier to track them. So there's one hydrogen on each of the carbons is colored in red, so we can keep track of the red ones, and the other four are all green. Okay? So to go from this eclipsed structure to this staggered structure requires one clockwise turn of 60 degrees, and we get the staggered structure. Okay? If we turn the front carbon 60 degrees again, up here we get a new eclipse structure, but this time one of the green hydrogens on the front is eclipsing one of the red hydrogens on the back. Okay? Turn it again, we get another staggered structure. Okay? And here in this case we have the two red hydrogens anti to one another. Okay? Another 60-degree turn. Okay? We come back to an eclipse structure, two more through one staggered down here, and we return to the original eclipse structure with the final turn around 60 degrees of that front carbon to where we started in the beginning. Okay? In ethane, which is a perfectly symmetrical molecule, we can see that the energy is minimized when all of the hydrogens are anti to each other, and it's maximized when all of the hydrogens are eclipsed. It's pretty easily visualized here with the red color shaded atoms. Every eclipsed conformer note in this structure is higher in energy than every staggered conformer, simply due to torsional strain. In any cases where we can get the adjacent sigma bonds as far away from each other as possible, we reduce the amount of strain related to torsion and stabilize the structure. Thus, the staggered conformer of ethane is more stable than the eclipsed conformer. Okay? Let's take a look at steric strain. Okay? Second type of strain, steric strain, refers once again to strain that's induced when atoms are brought too close together. Okay? Again, let's take a look at some experimental data to better understand this. So from the lab, okay, we know that the eclipsed conformer of butane is 14 kilojoules less stable than the anti-conformer. And if we think back to torsional strain, we might have anticipated this because once again, if bonds are overlapping, right, or eclipsing one another, that increases the energy of the entire molecule. However, notice we have one other piece of data. Okay, the Gauss conformation of butane is 3 kilojoules less stable than the anti. Now that should be sort of strange to us, okay? So we should assume that in all cases where butane assumes a staggered conformer, that it will always be equally more stable. But this is not the case. Whenever there's a Gauss interaction, we can see that it's destabilized. So something else has to be going on. The Gauss form of the staggered conformer of butane must have some other type of strain put on it that's not torsional strain because it's a staggered conformer, so there is no eclipsing bonds. Okay? Ask ourselves why. Okay? Why is this the case? If there's no torsional strain, how can it be that the Gauss conformation is destabilized? The answer is steric strain. Okay? Butane, which has two adjacent methyl groups, is destabilized when those methyl groups come into close proximity to each other. Okay? We're bringing the atoms close together, which destabilizes the molecule. Let's look at an energy diagram here. Okay? So this plot of energy versus dihedral angle will help us better understand this type of strain. Okay? Note here, we start in the upper left, we have the fully eclipsed form where the methyl groups on both the front and the back carbons in butane are perfectly eclipsing. Okay? This is the least stable conformation right here of a butane molecule. So we do a 60-degree clockwise rotation around that front carbon. This will bring us down here to a staggered conformer that has a gauche interaction between the front and the back methyl groups. Okay? Notice here, they're 60 degrees apart. This is a gauche interaction applicable only to a staggered conformer. Okay? Do another 60-degree turn, and we come into a new eclipsed conformer, right, up here. One more 60-degree turn of that front carbon, and we get the anti-staggered conformer in which the two largest groups are furthest away from each other. Okay? Because the molecule is symmetrical, the three other turns just create the identical conformers that we went through on the first three turns. Okay? So let's come back. Here, after the first 60-degree turn, okay, although torsional strain is eliminated because no bonds are eclipsed, recall it's the proximity of the hydrogen atoms to one another, right, on the front and the back methyl group, okay, that create additional strain. Namely, the nuclei in each of the hydrogens on the front and the back methyl groups are too close to each other, which puts the molecule into a higher energy state than it otherwise would be. Okay? The lowest energy state is in the anti-state when both the torsional strain is removed because no bonds are eclipsing one another, okay, as well as placing the methyl groups as far apart as they possibly can be, right, one pointing down and one pointing up on the back there, okay, making this the case in which steric strain is minimized as well. Again, building a model with your model kit of butane is the easiest way to visualize the interactions because you can actually pick up and handle the model and spin the bonds. So, as we've discussed, steric strain refers to the strain from atoms that are too close together, and torsional strain results from eclipsing sigma orbitals. The third and final type of strain is angle strain. For this course, we're only going to concern ourselves with angle strain applied to cyclic systems as first was proposed by Baer. So Baer hypothesized that ring structures force tetrahedral carbons to assume bond angles that match those of planar polygons. As such, he argued that rings create angle strain because they distort bond angles away from the ideal 109.5 angle of an sp3 hybridized carbon. Baer was onto something with the idea of angle strain, but it turns out his assumption that cycloalkanes are planar was wrong. So if we look on this slide from left to right, we see a series of cycloalkanes increasing in the number of carbons within the ring, going from cyclopropane to cyclobutane, cyclopentane, cyclohexane, cycloheptane, finally cyclooctane. If we want to compare the strain in each one of these alkanes, what we can do is consider the relative heats of combustion for each one of these. Okay? Heats of combustion for any particular compound increase as the number of carbon atoms increase. So we know they should go up linearly as we move from cyclopropane all the way to cyclooctane. What Baer proposed is that those cyclic structures that distort the internal bond angles further away from 109.5 will have higher heats of combustion than those cyclic structures that do not distort the rings. So let's just compare two of the rings from the homologous series that were on the previous slide. So according to Baer, cyclopentane in the upper left should be the most stable of all of our cycloalkanes because it has a cyclopentagonal shape. Okay? Pentagons have internal angles of 108 degrees, which is approximately the internal angles of cyclopentane. Okay? This is fairly close to the ideal bond angle of 109.5 degrees of an sp3 hybridized carbon. Therefore, according to Baer, cyclopentane should be the most stable cyclic structure because it has no angular distortion in it. Okay? In contrast, up on the upper right, planar cyclohexane would have bond angles much greater than 109.5 and therefore should be much higher in energy than cyclopentane should be. If we look at the experimental heats of combustion, however, we notice something very odd. So here we have the heat of combustion for cyclopentane, and if I divide the heat of combustion by the number of methylene groups that are in the ring, I get 658 kilojoules per mole per CH2 group that's in that ring. Look at cyclohexane, however. Cyclohexane is actually lower in energy than cyclopentane per CH2 group in the ring, which means that cyclohexane actually has less angle strain than cyclopentane. We have to look at the 3D structure of cyclohexane rings in order to understand where Baer got it right and where he got it wrong. In fact, let's look at cyclopropane, cyclobutane, cyclopentane, and cyclohexane in order to understand how ring strain or how cyclic structures create strain in the rings. Okay, cyclopropane. Here's a 3D model of cyclopropane. If we look at the 3D model, we can see that there are two sources of strain in this structure that we've talked about. One is angle strain. Cyclopropane truly is planar. It has torsional strain from 6 sets of eclipsing CH bonds. You can see them all around the ring, okay? And an enormous amount of angle strain from 3 acute internal angles of 60 degrees each. Cyclopropane distorts the carbon-carbon bond angles far away from 109.5, raising the overall energy of this structure. Here we have cyclobutane, but note what's interesting. Cyclobutane is not a planar square, but instead has a puckered shape to it, as you see on this slide. This non-planar conformer actually relieves some of the torsional strain by uneclipsing or staggering the adjacent CH bonds. They're offset from one another. The sigma bonds are not aligned. Angle strain in this structure is still present, however, because the bond angles are approximately 90 degrees still, even with the puckered shape. So we also have angle strain as well as torsional strain. Things start to get interesting, however, when we look at cyclopentane. It turns out that cyclopentane can assume two different non-planar conformers, the envelope conformer on the left and the half-chair conformer on the right. These two conformers actually relieve much of the torsional strain by offsetting almost all of the adjacent CH bonds in cyclopentane. Note that these two conformers are simply different spatial arrangements of the same molecule that has undergone internal sigma bond rotations. In fact, these two structures interconvert rapidly, which you can observe easily with your model kits. If you construct cyclopentane models, you can bend them back and forth, and you'll see you can create the envelope and the half-chair structures. Combined with an internal bond angle of 108 degrees, cyclopentane is much more stable than cyclopropane or cyclobutane due to the reduced torsional and angle strain in both of these conformers. The most interesting case is actually that of cyclohexane, which can assume many non-planar conformers, 3 of which I've shown here from left to right: the boat structure, the skew boat structure, and the infamous chair that you probably heard about before you even came into organic chemistry. Note that all of these conformers reduce angle strain and torsional strain that would be found in a planar hexagon if cyclohexane were actually flat. As with cyclopentane, these three structures interconvert rapidly from simple sigma bond rotations. Again, if you use your model kit, you can see how to convert one structure into the other simply by rotating bonds around one another. Of the three conformers, the chair conformer is by far the most stable. Using a model, you can see that all the adjacent carbons in the chair conformer are in a staggered conformation, thus eliminating all torsional strain completely. Additionally, the staggered conformation produces bond angles of 109.5 degrees, which is the ideal bond angle for sp3 hybridized carbons. Note as well that the staggered structure in simple cyclohexane rings has all of the hydrogen atoms gauche to one another, right? No steric strain occurs in the structure, right? We'll focus solely on the chair conformer in our course this semester. Although the other conformers are interesting, the chair is the most useful to help us better understand all three types of strain in a cycloalkane. So, in the next lecture, we're going to closely examine the relative stability of different cyclohexane derivatives. But to help us do that, it's important you understand how to recognize the chair conformers in drawings and to differentiate between atoms that are spatially distributed in chair conformers, which we'll end this pre-lecture with here today. So, if we look at a molecular model of a cyclohexane ring, we can divide all 12 bonds around the ring, all 12 CH bonds, okay, into two sets of 6. And on the next few images, I'm just going to color code these and remove some bonds so we can highlight the two sets of 6. Okay, so here, 6 of the bonds are called axial bonds. Okay, 3 of them point up on the slide and 3 of them point down. I've removed 6 of the other hydrogens just to highlight the 6 axial bonds. Okay, 6 axial bonds, 3 pointing up, 3 pointing down. Okay. There are also 6 equatorial bonds going around the ring. Okay? All of these bonds are said to lie around the equator of the ring. They're all displayed outward from the ring. Okay? There are 6 equatorial bonds. Again, 3 of them point upward, 3 of them point downward, and you can see they point up and down in alternating patterns around the ring. Right? Here up, here down, up, down, up, down. Right? 3 up, 3 down equatorial CH bonds. Okay. The two conformations of cyclohexane chair structures interconvert rapidly the same way in which the cyclopentane conformers interconvert rapidly. However, in this case, it's important to distinguish between the axial and the equatorial bonds in a cyclohexane ring. Up on the left, in this structure, I've colored all of the axial bonds in the conformer green and all of the equatorial bonds red. Okay? Through simple sigma bond rotations, I can create an alternative chair conformer in which all of the equatorial bonds have become axial. Notice that the red equatorial bonds from the first image have now become axial bonds, and the green axial bonds in the original image have become equatorial. This did not involve breaking any bonds whatsoever, right? So it is not the case that we pulled off the greens and pulled off the reds and switched places. Through simple sigma bond rotations in the cyclohexane ring, we created a new conformer from an old conformer. Okay? The most helpful thing you can do is to take your molecular modeling kit, construct a 6-membered ring, put hydrogens on it in the axial positions only, leave the equatorial ones off, and then twist the ring in such a way that you move all of the axial positions to the equatorial positions, and you see how this happens without breaking any bonds at all. Okay? In your book and on the future slides, you will see the molecular models depicted in 2-dimensional diagrams that look like this. Okay? Here are the two chair structures, or the chair conformers of cyclohexane rings shown to you in molecular models, and here they are drawn out in 2-dimensional diagrams. Notice the similarities between the shape of the diagram and the shape of the molecular model. Right? To the left, this part of the ring is pointing down, as is it here in the diagram. To the right, this portion of the model is pointing upward, right, as it is here in the diagram. Notice in the diagram, I've not drawn any of the axial or equatorial hydrogens. I've just drawn the carbon atoms around the ring. However, we know, of course, that the hydrogens are still there. We just haven't drawn them. A lot of students find it helpful to shade the front three bonds, okay, of the cyclohexane ring to just give them a bit of perspective so you can see that these three bonds are actually closer to you than the three bonds in the back, as they are here with the lighted shading of the molecular model. Same thing is true down here with the second set of the other chair conformer of this ring. Okay, in this case, the left side is pointing up, so the left side of the diagram points up. The right side of the diagram is pointing down, so the right side of the, the right side of the model is pointing down, so the right side of the diagram is pointing down. Okay. Once again, we haven't drawn any of the axial equatorial bonds. Here it is shaded, so you can see which side is pointing at you, and the back is not shaded. Okay. Here's a boat structure just for reference. Remember, we're going to spend most of our time concentrating on chairs, but to recognize a boat in a diagram, which you will see in your book, here it is in the molecular model. In this case, both ends or both tips of the cyclohexane ring are pointing in the same direction. They're both pointing up. Here's what it looks like in a 2D diagram. Note that for perspective, we cut the backbone with the front bond here to give us the illusion that this bond is in front of the other bond behind it, but it's not actually broken. Okay? And here it is drawn with the shading. Take some time on your own to practice drawing chairs in 2D, because that's how you're going to have to produce them on any assessments in the class, and that's how they're going to be shown to you in the textbook. Again, building this with your molecular model is the best thing you can do to get better at recognizing which bonds are axial and which are equatorial, and we'll spend a significant amount of time in class together working with our models to understand these relationships. With that, that is all I have for you for this pre-lecture. As always, make sure that you review the relevant reading in the Carey textbook and come to class prepared to apply what you know. Note that for Tuesday's class, we will be collecting points for the clicker questions for the first time of the semester, since this is week 3. So make sure you review and come prepared to answer questions to the best of your ability.